All right. Let me begin with a word of prayer. It's time to start, and then some. Dearly Father, we thank you for this day. Again, I thank you for this class, for these students. Just ask you to just bless our work today. Help us to, again, glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. Amen. All right, so today I will talk to you guys about function operations. Or you might say new functions from old. Sometimes I title that this. And so basically the point is if we're given functions f and g, then we define f plus g of x, we define f minus g of x, we define f times g of x, we define f over g of x, and last but not least we define f composed with g of x, and we'll also define g composed with f of x here, okay? So each one of these is some new kind of function we can build from a given pair of functions, all right? I'm talking about the sum, the difference, the product, the quotient, and then the composite in either order.
Oh, the composite.
The composite, right. So this one's pretty easy. This is just f of x plus g of x. Then we've got f of x minus g of x, f of x times g of x, f of x divided by g of x. Now what's the condition here? We need g of x to be what? Is assumed to be not equal to 0, right? If g of x is equal to 0, well, we're out of luck there, right? Now, how about f composed with g of x? What does this mean? This here means that we're taking f of g of x. So we're literally plugging the formula for g into the formula for f. Now, there is a term and condition here. We need that g of x is an element of the domain of f of x. See, if I don't know, excuse me, goodness gracious, we do need in order to make this make sense, we need the value g of x is actually in the domain of f of x for that to make sense. And last but not least here, g of f of x, all right, is g composed with f is g of f of x. And here, for this to make sense, we need that f of x is an element of the domain of g of x. All right, so that's the fine print there. So let's look at an example. And I'll start out symbolic, all right? I'll start with a symbolic example. So let's suppose we have f of x equals to x squared plus 2, all right? And we have g of x is equal to the square root of x plus 1. You guys with me so far?
I'm with you.
Michael's with me, all right, good. So what would f plus g of x be equal to?
F of g plus x.
F plus g of x is equal to? So we
x squared plus 2
plus
the square root of x plus 1.
Correct. And so you're like, okay, is that it? What's the point? Well, the point is we can do this. We can add functions, all right? And the subtraction is similar, f minus g of x is equal to what? Well, x squared plus 2 minus the square root of x plus 1. So there you go, there's that one. How about the product? Pretty simple, right?
Yeah.
fg of x, we just multiply f of x, which was x squared plus 2, times the square root of x plus 1, and I mean, that's it. That's it. And what's the quotient? Well, the quotient, f over g, what do we got? We've got x squared plus 2 divided by the square root of x plus 1. Now is where it's about to get interesting. The composite, we got to think a little bit more about. And it's helpful to have some language for the composite. So listen, I call this is the inside function. Inside function, right? In this case, g is the outside function. So we have an inside function, we have an outside function. All right? And the difference matters. So let's look at it this way. If we have f of g of x, we can write that as f of, let's say, u, where u is equal to g of x. All right? And then what is it? If we put a u into the formula for f, what do we get? See that? F of u is u squared plus 2. Right? But what is g of x here? The square root of x plus 1, right? So this is literally the square root of x plus 1, quantity squared, plus 2. So in this particular case, I could simplify, right? What would the formula, how'd that formula simplify? We get what? Just x plus 1 plus 2, or in this case, x plus 3 would be a nice answer. I don't usually worry about simplifying too much with these, but since it was so obvious, I decided I would do it here. All right?
Got it?
Got it? All right. Let us try. I'm gonna put it up in here, guys, if you don't mind. What is g composed with f? How's that go? So that is g of f of x, all right? But here, let's say that that's g of u, where u is equal to f of x. What is f of x equal to? It is x squared plus 2, right? So what is g of u? Well, g of u is the square root of u plus 1. Right? Now, I don't want to leave it like that. I need to plug in what the u is. It's x squared plus 2 in this case. So we end up with the square root of x squared plus 2 plus 1, which is 3, right? Question, what would, instead of, what if I did gf of x? What would gf of x be? Notice that this would also be equal to the square root of x plus 1 times x squared plus 2
Equals.
So that would be literally g f of x. So I want to
Don't worry, I got it. I got it.
Okay, I want to point out something to you, which is that when we take the product of functions one way, or if we take the product of functions another way, it's equal. Because the product of functions is defined just by multiplying the formulas. And multiplication commutes. However, substituting the formula for one function into the other function, that does not commute. As you can see, f composed with g of x gave me this formula, right? Whereas g composed with f of x gave me that formula. Are these equal? They are not, right? So it matters which order you're doing it in, and you have to work through it. Let's look at another example. Unless there's a question.
Why are they not in order, Professor Cook?
Not in order. What do you mean?
composite ofs, how you decide the order of.
Why does the order? Because we're plugging the formula for one function into another, and it's just not. It doesn't work out the same if we do it in a different order. All right, so let's look at another one. This one I'm going to make. I'm going to make this next one so we don't have formulas. We have like a table of values, let's say. All right, so because we haven't done this yet, so it'd probably be good for me to talk a little bit about this. We could have, let's see here, we could have x, all right, and we could have f of x, we could have g of x, all right, so we can have 1 here, and I could have 2 here like this, right? And I guess I could put a 3 over here like that, right? And I could fill in this and give some values here, like I could put, oh, I don't know, 3 and -1 and 0 and 2 and 6 and 7. Yes, Michael?
Is this problem related to problem number 59?
I really don't know right offhand. But so, what is f plus g of 1 equal to here? Let's just try some out here. Well, you guys know the definition. It's f of 1 plus g of 1, right? But what is f of 1 and g of 1 from the table? Can you tell me?
-2.
F of 1 is what? If f of 1 is
Positive 2.
f of 1 is 3, g of 1 is -1. So I think someone told me 2 a second ago. That would be correct. Very good. What would f g of 2 be equal to? Well, by definition, that would be f of 2 times g of 2, right? Which would be what in this case? Yeah, we've got a 0 times, well, who cares, right? So 0 times 2. So that would give us 0. Let's see here. What if we tried g composed with f of 1? What would that be equal to? By definition, that's what? G of f of 1. What is f of 1 equal to?
-3.
No, f of 1 is 3 here.
Oh, it's a composite.
Yes, this is not the product.
Oh, whoops, sorry.
That's okay. That's the point of this one.
Equals
G of 3.
F1.
So notice for the composite, we're not just taking the numbers in the table and multiplying, right? We actually have to think through which one goes to which one, right? It's not a sum or a difference or a product. You have to think through it. G of 3, which is 7, right? Correct. And let's see here. How about let's see here. F composed with G of 2. What would that be equal to? Let's see, so we've got f of g of 2, which is what? What is g of 2? G of 2 is equal to 2. So we have f of 2. What is f of 2 equal to? Well, 0. There you go. Now, another interesting question that you can ask is, like, graphically, what do these different things mean? And I don't have anything nice to tell you, really. about how to graph the product of functions or the quotient or even the composite. I don't have anything nice and simple to tell you about what that means graphically. But the sum of two functions is pretty easy to understand graphically. So like, let me show you an example of that. All right, so like, and this is maybe the only place I'll talk about this kind of thing. So this might be a function, right? So here's y equals f of x. And I might have another function which is formed by the reflection of that across the x-axis. So it might look like this. Here's y equals to g of x. Okay? So for this example, something kind of interesting happens if we add the functions. Like what is f plus g of x equal to? What's f of x plus g of x equal to for this example? Right, so like so for example, if I make this at say 2 and this is at minus 2, right? And let's suppose this is at 1. So we've got like g, for example, g of 1 is minus 2, whereas up here f of 1 is equal to 2. Ooh. Let's see, which room am I in? No, never mind. It's just the other board. Just the instructor on the other side. I could theorize who that was. But anyway, like somebody said a second ago, that would be 0, right? Because they're equal and opposite, they cancel out, right? So if my graph was done carefully, my claim is this would be 0 for each x. So like the sum of these two functions is what? Just, it's kind of a boring function, right?
2 plus negative 2.
2 plus negative 2 is 0, right? So that gives us this point right here. But the graph of the sum function is just this guy. See that? Y equals to f of x plus g of x is just equal to 0 for this example. Do any of you guys have, yeah?
So not necessarily like about the actual problem, but like how does the composite of like f and g, how does that really like apply to real life?
How does the composite apply to real life?
Yeah.
Do you believe you exist?
Yes.
You will be calculating composites on the next test in here.
Okay.
That is the most relevant example. But that's not the answer you're looking for, but it's the answer I always give. An example where composite might be interesting is something like well, I always think of physics, so you know, if I reparameterized a path, that would be like composing my original path with a different sort of what's the word? Choice of trajectory. So you know, that composition would correspond to like going through the same set of points but at a different speed or something. But really composition is just when you put two things together. Like anytime you have two things that interact with each other, you're talking about a composition of one function and another. So if you can think of two things that depend on each other and are both a function, you can think about composition there. Like, oh, I don't know. You've got a store that sells widgets, and you've got a bus that stops in front of the store, right? So the number of widgets that it sells is depending on the number of people that enter the store, right? Well, that would depend on the number of buses that come by in front of the store. So you could look at like a composition of like the bus function with the widget selling function to come up with like a number of widgets sold function or something like that. I don't know. You could come up with better examples, I'm sure. But, but my first answer was a better answer. Okay, so hey guys, this is new functions from old. This, I didn't finish this story here. This is an example of what's called destructive interference. If you have two waves and you add them together and they just cancel out, that's completely destructive interference. So here, x would more properly be like time, and you're looking at a wave through time. This is how noise canceling headphones work, right? They add in like anti-noise against the noise in the room, and it cancels out and makes it quiet, something like that. It's also the principle that comes up by making, like, you've seen oil films have like colors of on bubbles, different rainbow colors. That comes from like different frequencies of light canceling out through destructive interference in terms of the reflection off the front of the film and the back of the film, and the way the waves end up like that or not like that. The other thing that can happen is when they're the same, they add together and make the same kind of wave bigger. All of that is function addition. But yes, Michael?
It's kind of like the DNA.
Yeah, that does look like DNA. That's true. Now, don't ask me what that means, because I surely don't know. But
It's like the DNA of functions.
In the sense that it's shaped like a double helix, sure, but nothing else.
okay, so that's it for functions. I'm going to go on now.
All right. Problem number 59, I hope.
We shall see, Michael. So,
Eager.
So my next question for you is, what is 5,342? 5,342 divided by, oh, I don't know, 25.
Oh. Oh, I know this.
See if you can figure that out. Yes, Michael.
213 with a remainder of 17.
213.
With a remainder of 17.
Remainder 17. All right, I'm putting that down for the record. I hope you're right. We'll find out soon. But actually, in this particular case, I'm more interested in the process than I am the answer. All right, so let's think through this. Do you guys remember? Well, here, I'll show you how I was taught to do this. I start by looking at this here. How many times can I put 25 into 53?
2.
2. So that brings a 50 down here. I subtract it, right? And that gives me a 34. And then, how many times can 25 go into 34? Just once. So I subtract 1 times 25, also known as 25. 34 minus 25 is 9. I bring down my 2. All right. How many times does 25 go into 92? 3. Michael, this is looking good. 3 times 25 is 75. All right. I subtract it, and I get what? 17. Hey, cool. Very good, Michael. So, what's that?
Did you want the decimal or?
No, we don't want decimals. And let me show you why. So, yes, this is 213, remainder 17. What does this calculation mean in terms of arithmetic? So this means that 5,342 divided by 25, right, is equal to what? It's equal to 213 plus 17 over 25, right? That's what this calculation means. Another way to look at it is that this means that 5,342 is equal to 213 times 25 plus 17. That's another way we could look at this calculation. Now you might wonder what on earth that has to do with this class, right? Well, the answer is that's the same pattern that we use for polynomial long division. Yes, polynomial long division. That's not usually the reaction I get, but I'll allow it. Let's see here. Polynomial long division.
Oh.
So let's try out one of these. So here we go. 4x to the fourth power plus 3x cubed, all right, plus, let's say, 2x squared plus x plus 1. All right, that's ugly enough.
Yep.
And
this matches my problem.
oh, did I make up the same problem?
5x.
Someone's like, shh.
Well, f of x equals 5x.
It's not quite the same, but
I just wanted to know an example. That's all.
okay, well,
Same pattern of problem.
it may be the same pattern. I'm a creature of habit. All right. So let us divide something into it. For example, I will use x cubed plus 3, not x cubed, my bad, x squared plus 3x plus 2. We'll divide this into that. So the way this works is we have to pick on the biggest thing that's there. In this case is 4x to the fourth. The question is, how can I get a 4x to the fourth from this? What should I multiply this by? This divisor, x squared plus 3x plus 2. What do I need to multiply that by to get a 4x to the fourth? I heard a 4x.
Oh, you need to put the left side to the factorist.
Well, no factor in here. No factor in. So this is all about multiplying. So 4x squared times x squared plus 3x plus 2. What's that give us?
X squared plus 3.
That gives us 4x to the fourth plus 12x cubed plus 8x squared.
4.
So the reason
New sheet.
that we wrote 4x squared here is to match this 4x to the fourth. All right. So I multiply the divisor by what I put here, and I put that here. So I got 4x to the fourth plus 12x cubed
Plus x3
plus 8x squared.
X squared plus x plus 1.
And now we subtract, just like we did over here, right? We figure out what the multiple of the divisor is. We subtract it from the biggest thing. Doing the same thing.
4x 4. Oh, hold on. Let me write this down. I'm far behind.
So when we subtract here,
I don't-
Michael, you have to stop talking during class, man.
Sorry,
Okay.
I'm so sorry.
Okay. So we subtract. 13 minus 4 minus 4 is 0. 3 minus 12 is minus 9x cubed. 2 minus 8 minus 6x squared. All right? And then one thing that's a little bit different about polynomial long division versus the regular division is it helps to bring everything down at this point. So like when I do this first subtraction, I bring down the x and the 1 as well. So plus x plus 1. All right? Because that's what's left. I'm trying to get rid of it, okay? So then the question is, looking at the divisor, here x squared plus 3x plus 2, what multiple of this do I need to get rid of the biggest thing?
3x3.
3x3? 3x3. How about I'll trade you your 3x3 for a minus 9x.
Minus 9x.
See, because if I have minus 9x times x squared plus 3x plus 2, what do I get? Minus 9x cubed minus 27x squared minus 18x. So that's why I'm going to put a minus 9x up here. All right? And when I do that, I multiply the 9x times the x squared plus 3x plus 2. Right, I did over here, and I put that down here. Minus 9x cubed minus 27x squared minus 18x. Now I got to be careful. I put some parentheses here, guys, just to emphasize that I have to subtract all of that. All right? We have to mind the signs. So the minus 9 minus a minus gives me 0. That's the whole idea. What is 6 minus a minus 27?
Negative 33x squared.
But it's minus a minus, Michael, so it's...
Oh.
It's minus minus is addition.
So we got 21x
21x squared
21x squared, right?
plus 19x.
Plus 19x, yeah. Plus 1.
Oh, sorry.
It's okay. Now, how did we know we were done in the other calculation? What made 17 the remainder?
It can't be divisible by 25.
Right, exactly. Well, another way to say that would be 17 is smaller than 25, right? When you get to a number which is smaller than 25, you're done. Right? How about over here? What am I looking for? I'm looking for something that is of smaller degree than this. I'm not there yet, see, because this is order 2 and this is order 2. There's still hope of subtracting some multiple of this off of that. What's my next one?
2x squared.
2x squared now. But you see, Michael, what we're trying to do is we're trying to get rid of this right here, right? So what we're going to do is we're going to say plus...
This is our main target.
That's right, plus 20... Well, man, plus 21. My apologies, I seem to have written something in the hideous Carolina blue. But it's not dead yet, so I guess if I want it to go away, I have to keep using it, right? See, so 21 times x squared plus 3x plus 2. What's that equal to? Well, that's 21x squared plus 3 times 21 is 63, right? Plus 42. So that's what makes me put a, excuse me, 21x squared plus 63x plus 42 down here.
Oh,
We have to subtract that. So when we subtract that, what happens? Well, the 21x squared cancels, all right? And what's 19 minus 63? 44, minus 44x. And what's 1 minus 42? Well, it's
minus 41.
minus 41. At this point, this right here is the so-called remainder. Why is that? Because this has degree 1, whereas our divisor had degree 2. All right? And what does this calculation mean? Let me tell you what it means. It means that 4x to the 4th plus 3x cubed plus 2x squared plus x plus 1 can be written, in fact, as 4x squared minus 9x plus 21 parentheses times our divisor, x squared plus 3x plus 2 plus the remainder. That's what this long division means.
S squared.
So here's a question that we can ask once we've done this, is is x squared plus 3x plus 2 a divisor? Well, let me not say that. Let's say, is it a factor of f of x? Where I'm defining f of x to be this. What do you guys think the answer to that is?
F of x equals...
What would it mean for it to be a factor? That would mean that you could factor it out, right? Can we do that?
Oh, yeah.
I don't think we can, though, because
Dang.
we have a remainder.
We can't factor.
Yeah. So there you go. That's example, I guess that's example 4 for me today.
Wow. What a long example.
Yes, Michael.
I'll figure it out.
That's good. So, unfortunately, your book is pretty sparse on this. Like, it doesn't have much at all, really. So I do have a handout for the polynomial long division, which I might have already put in Canvas, but if I didn't, I will soon and make an announcement about it. But I have an example. I have a PDF where I have about like 10 long examples of this so that you get more. I mean, we're going to do more examples in class, of course, but this is not hard, but it does require attention to detail, right? You have to be careful. There's a lot of places to make mistakes. But you can do this if you practice a bit. Let's try another one. So let's take x cubed rather, plus 3x squared plus 3x plus 1. And let's try to divide in x plus 1. Let's see how that goes. I'm going to write a little bit less in this example. Like, I don't usually, this stuff I wrote on the side, this side work here and the previous one, I don't always write that down. Especially when it's easier like this one. So, in other words, what do I need here to get rid of the x cubed? What should I write? Yeah?
X squared.
X squared, very good. Nope, stop there, right there. Just x squared, that's all we want. Now, what is x squared times x plus 1?
X cubed plus x squared.
X cubed plus what?
X squared.
Plus x squared, okay, great.
Plus.
Then we subtract. I guess I'll write the side work again. So what I'm doing is x squared times x plus 1. That's what I'm subtracting, right? See that? Now we subtract. What do we get?
X squared plus 2x squared plus 3x plus 1.
Very good. That is, in fact, the right thing to do. Now, how do I get rid of 2x squared with x plus 1? What should I next divide by? Yeah, Michael?
I believe you need to divide by, according to my calculations, 2x times x plus 1.
So, I will take your, yes, 2x will do. Very good. All right, so plus 2x, plus 2x is what we want here. Now, 2x, what is 2x times x plus 1?
2x squared plus 2x.
Right.
Oh, don't forget to subtract.
That's right. Well, that's the next step here. We subtract that. So subtract that. What do we got?
X plus 1.
All right. So how do we get rid of x plus 1?
Oh, it's the same.
Plus 1, right.
X
Plus 1.
Ah.
All right. Now we put x plus 1 down here. What's my remainder?
Nothing.
X plus
It's nice and happy.
x
Right.
minus
So what does all this mean? This means that,
no remainder.
that's right, so x cubed plus 3x squared plus 3x plus 1 is actually equal to x squared plus 2x plus 1 times x plus 1. Or if you prefer, you could also understand this in terms of x cubed plus 3x squared plus 3x plus 1 divided by x plus 1 is in fact equal to x squared plus 2x plus 1. So follow-up question, is x plus 1 a factor of f of x?
Yes, it is.
Yeah, it is. And by the way, can you factor f of x completely here?
Yes, yes, we can.
What is it?
Huh. Hold on.
So what is this actually? This silly example? X plus 1 cubed, yeah.
Oh, don't forget to completely factor.
Yeah.
That was a good example.
It is more fun. It is more fun when the remainder works out to 0, isn't it? Yeah, it feels good. Let's see here. Example 6. Try to come up with something here for you guys. So let's suppose that f of x is equal to I'm getting there, guys. Just a second. I'm planning,
Don't worry, I'm teaming up.
plotting against you guys, but in a good way. So x to the 4th plus 6x cubed plus 6x squared plus 6x plus 5. I hope that I got it right. All right. Let me just double check that right quick. Kind of close to it. Okay. And you're given that f of I is equal to 0. Factor f of x completely over the reals. See, this is a problem that we worked before, but now we have a new tool at our disposal. All right? So first of all, what did the complex factor theorem tell us? Do you guys remember? Remember this? I had this theorem, f of alpha plus I beta equals to 0 means that x minus alpha squared plus beta squared is factor. So in this case, I'm just giving you that f of I equals to 0, right? So identify then my alpha is equal to 0, my beta is equal to 1. So this simply gives us x squared plus 1 is a factor, right? X squared plus 1 is a factor. So we should be able to factor it out. Now we can do that with long division. So what I'm interested in then is x to the 4th plus 6x cubed plus 6x squared plus 6, wow, this has got 666 in it, doesn't it? Let's see here, plus 5. Never mind that. X squared plus, there's x's there, so it makes it better. Okay, so we want to divide. This example, this whole lecture is very divisive. If you know, it's like, all right. So we got What we got here?
X squared.
X squared, I think we that's correct. We got x squared to start with.
Plus
Now, I multiply x squared times x squared plus 1. That gives me x to the fourth. Now watch this. I want to put it where it belongs. Where does x squared belong?
X squared plus
Over here, right? Now you can write it wherever you want, but it's better to put it under the x squared term just to make sure you don't make the silly mistake of subtracting x squared from x cubed, as if you could do that, right? We can only subtract like powers. We can subtract squares from squares, cubes from cubes, linear from linear, but we can't subtract unlike powers, apples and oranges, right? Let's see here. So that gives us a 6x cubed plus 5x squared plus 6x plus 5. All right. Next up, plus 6x. All right. So 6x times x squared plus 1 gives me 6x cubed plus 6x. I should probably put that over here. And I subtract again. What do I get from that? Well, I get myself a
5x squared plus 5.
Very good. That is correct. And so what should I add to get rid of the 5x squared? Plus 5. So if you're one of the people right now who's getting it, great. If you're one of the people who doesn't understand where these magical responses are coming from, don't feel bad. You will join them soon. Just work at it. It will happen for you too. So 5 times x squared, we got 5x squared plus 5.
It can be factored.
It had better be able to be factored. Otherwise, what you were given was junk, which would be bad on my part if I told you that it was a 0 and it wasn't. But yeah, it's a 0. So the remainder is 0. What's this mean?
It can be factored.
It can be factored. This specifically means that f of x is actually equal to x squared plus 6x plus 5 times x squared plus 1.
Plus 1.
Now, before this, we had to do some kind of funny business with equating coefficients. It took us a little work. Now we just do long division, and we've almost got the answer. Almost done. What do we do now?
Factor it.
Is it factored completely yet?
No.
What do we still need to do?
There's 4 x's.
Well, x squared plus 1 can't be factored. That's prime, right?
Oh.
Because that comes from the f of I being 0. It's a irreducible quadratic, as we say. 2 and 3? But 2 times 3 is 6. 1 and 5. Yeah, x plus 1, x plus 1, x plus 5. There you go, completely factored. And that is how we can use long division to help us factor. We'll do more of this Monday.
Well, today's math class was very professional.
Very professional.